And it's my great pleasure to introduce our today's speaker, Professor Simon, Barry Simon from California Tech, and the title of his talk is on the screen. So many thanks, Professor Simon, for agreeing to deliver a talk at our seminar, and please go ahead. Thank you.
Okay, so thank you for the invitation. It's a pleasure to give this talk. You see the title. So last year, we celebrated Elliot Lieb's 90th birthday. On Friday, January 14th, 2022, I had a draft of a single-authored paper intended for a festschrift to be published for Lieb's birthday. 6 days later, the paper had 3 co-authors who I hadn't met before January 14th. Indeed, even now, I've only met them on Zoom. This talk will explain the interesting story behind this, expose some underlying machinery, sketch the proof of a lovely inequality on certain finite sums. It will include an improvement of 50-year-old bounds of Griffiths, comparing transition temperatures on generalized Ising models for different spins. I'm writing a book for Cambridge Press that's entitled Phase Transitions in the Theory of Lattice Gases. It's in many ways the successor to my old book from Princeton Press entitled Physical Mechanics of Lattice Gases, Volume 1, but the earlier book was mainly framework, largely left out most of the fun and beautiful elements, correlation inequalities, Li-Yang, pyrals, infrared bounds, random clusters, and currents, which are the subjects of the new book. But since I decided to use a different publisher, you'll notice it's certainly not volume 2 of the earlier work. So let me explain the framework that I'm going to be discussing today. One fixes a fixed finite set in the integral lattice in new dimensions, and an even a priori measure on the real line. Certainly it has to have all moments finite. Somehow it's not showing the bottom line. It has to have all moments finite. Typically, it's of compact support. One considers configurations in this finite set lambda, that is points sigma in R to the lambda that are indicated by sigma j. So sigma j is the jth spin. It's the spin value. It's a real number at the point j in lambda. And you take the uncoupled measure on these spins. That's just the product measures formed with this even a priori measure. And you fix a ferromagnetic Hamiltonian. So sigma A just means the product of, for J and A of sigma J. Ferromagnetic means the JAs are positive. And one considers the Gibbs state formed from the Hamiltonian in the usual way. One typically studies infinite volume limits with a translation invariant A, but you normally study it by proving stuff about finite volume expectations. And so in my talk today, I'm going to entirely discuss finite volume expectations. Traditional cases, of course, the classical Ising model, sometimes called the spin-a-half Ising model, where the measure has just 2 points. It's supported at 2 points plus or minus 1, each with weight a half. But more generally, I'm going to consider at one point, I'm going to consider much more general measures, but I'm going to also want to consider the case where we have 2 points, but instead of being plus or minus 1, plus or minus t, I'll call this BT. B is for Bernoulli. A lot of literature is for spin-a-half, but there's a lot of mathematically interesting literature for more general, even a priori measures. As I began writing about the subject of correlation inequalities, I wondered about a natural question. Say you have an a priori measure nu, two of them, nu and mu, two different a priori measures, and say that nu Ising dominates mu. Whoops. If and only if you have the inequality you see on the bottom for all possible sets B. In particular, for mu of compact support, one wants to know if you can sandwich a given mu in terms of a BT minus and a BT plus, because in particular, that would say that if you had phase transitions for mu, you'd have them for spin a half, and if you have phase transitions for spin a half, you get it for mu, and it gives you relations between transition temperatures. To be explicit, if mu dominates, Ising dominates BT minus, and BTC is a transition temperature, and you have just pair interactions in the Ising model, you get a lower bound on the transition temperature for the general measure mu in terms of classical Ising. For even minor aspects of the subject of correlation inequalities, there are normally several papers, often dozens, and I was surprised I was unable to find a single published paper on the subject of what I just called Ising domination. Of course, it was unclear how to search for the subject on Google. Eventually, I did find one paper of Van Byron and Sylvester that's unsatisfactory in that, in their theory, the analog of what I'll call T minus is 0 if this measure mu has 0 in its support, and in particular, if say mu is supported at 0 plus or minus 1 with weight of third, so-called spin 1 Ising model, they get no results. I did also find an appendix of a paper on another subject that gets ahead of my story. One of the pleasant things about writing a book on a subject I once knew more about is that I get to rediscover things I've forgotten. With the question of Ising domination of the back in my mind, I found an interesting footnote in a paper of Michael Eisenman and me entitled "A Comparison of Plane Rotor and Ising Models." And the footnote in the paper said the following: by results of Wells, and there's a reference to a preprint of Wells, one has the inequality on the screen where the left-hand side is an Ising expectation. That's what the sub 1 means next to the beta. And the right-hand side is actually a situation where the measures are from 2D rotor models, but the couplings of the rotors are only the one component. So this is exactly this generalized model, but the a priori measure is the distribution of one component of a uniformly distributed two-dimensional spin on the circle. And the 2 indicates that it's a 2-component measure. So I went about trying to find Wells' preprint. Google didn't help, but it did point me to a 1984 paper of Chuck Newman that mentioned Wells' Indiana University PhD thesis. So I wrote to Michael, CCing Chuck, asking if he knew anything about our footnote. And I wrote to Chuck because I conjectured Wells had been his student, because this was at a point when Chuck was at Indiana. He replied that he remembered Wells had in fact been Slim Sherman's student. Sherman is the S of GKS and GHS inequalities. Delightful person, long dead. So I wrote to Kevin Pilgrim, the chair at Indiana, who located a copy of Wells' thesis for me on ProQuest, but he had no luck on the preprint, nor on locating Wells through Indiana University alumni records. I should point out, to get way ahead of my story, when I eventually did make contact with Wells, mentioned this to Wells, Wells said, that's strange because I keep getting fundraising solicitations from them, so they must have my address. While the thesis didn't have anything directly about the above inequality, it had a general framework on what I call Ising domination, something that should have been published but had not been. Our first goal in this talk is to describe Wells' framework and what I regard as his most significant theorem. Since he extended a framework of Genève, I'll begin by reminding or telling you of that framework. Then I'll talk about this notion of Wells' domination, followed by the big theorem from his thesis. Some examples, including a conjecture relating to spin S, and I'll tell the story about proving the conjecture and locating Wells. Finally, I'll sketch a proof of the conjecture in as much detail as time allows. So in 1970, Jean Genève, who fortunately passed away a little over a year and a half ago, not only found a really simple proof of GKS inequalities, but found somewhat surprisingly, they actually held for all even a priori measures. If you're doing it to Ising models, have time for only one result, you should really understand Genève's proof because it's elegant, beautiful, and deep mathematics. So what I call a Genève system is a triple consisting of a compact Hausdorff space, a probability measure with expectations, and a class of continuous real-valued functions f that obey the two inequalities on the screen. The integral of a product of n functions from this class f is positive, and you get, if you take a double integral of the n-fold product with arbitrary choices of there are 2 to the n sign choices in the product that are possible. You can have any combination of pluses and minus. All those have to be positive. When it's clear what measures intended, I'll drop the mu from expectation. I've restricted the compact Hausdorff, but it works just as well for things with finite measures, finite moments. I want to note that this second inequality actually implies that expectations are positive because twice the expectation value of f is just that integral. And it implies that the correlations are positive because if I take just 2 products with both minus signs and you write out the integrals, you just get twice the correlation. What makes the notion so powerful is that there are 3 theorems for getting new Genève systems from old ones. Given a family f of functions, I define the Genève cone as the set of linear combinations with non-negative coefficients of products of functions from f. And the first big theorem is that if you have a triple, Genève triple, you can replace f by its Genève cone, and it still obeys this second inequality. And of course, that's trivial for sums and positive multiples. It's products that are non-trivial, but by repeated use of that formula on the screen, it's easy to show that you can handle products of 2 functions, and then by inductions, products of n functions. So the reason one wants to handle n-fold products with arbitrary choices of plus and minus is because you want to multiply use the formula that's sitting on the screen. And that'll let you prove G2 for a single product and then for multiple products. Second theorem is totally trivial. If you have a family of Genève systems and you take their product, and you take the union of the f's, it's also a Genève system. So in particular, if you start out with a family of Genève systems, you can take products, and the last of the big three theorems is that you can also change your measure by going from mu to a Gibbs measure, given by the formula sitting there. And the proof really is you write out in the twofold product, you expand the exponential, because minus h is supposed to be an f. It's the integrals you get are exactly these n-fold products. And so again, you get that the Gibbs measure is Genève. And the fourth theorem that Genève proved is that if you have an arbitrary even measure on R, and you take f just to be the single function x, and you take a probability measure which is even under sign flip under changing x to minus x, then this triple is a Genève system. And the proof is easy. Really, what the theorem says is these integrals all have to be positive. If you interchange x and y, you see the integral is 0 if m is odd. And if you change both the sign of x and y, you see the integral is 0 if m plus k is odd. So the only way the integral can be non-zero is if m is even and m plus k is even. And in that case, the integrand is positive because k and m are both even. So of course the integral is positive. So you think about it a second, in these 2 slides or 3 slides, I've proven positive correlations for Gibbs measures formed by arbitrary ferromagnetic interactions with an arbitrary even measure. That's this wonderful paper of Genève. And I'm going to skip these because I'm running a little late. I'm going to skip some slides. So Wells had the following idea of extending Genève. He considers 2 measures, and we will say, he didn't obviously call it Wells domination. We'll say mu Wells dominates nu if we have product integrals like what Genève wrote down, but we now have different measures, mu and nu, and the mu is associated with the thing that has all plus signs. The nu can have plus or minus signs, and that what makes this non-symmetric. You can say if this is true, you get that mu dominates nu, and we'll mainly be interested in the case where mu and nu are even measures on R, and f consists of a single function, in which case the domination condition is just the positivity that's sitting there. Since the measures are even, you only need to check this when n plus m is even. When they're both even, it's trivial. So really what you need to do is check this when n and m are odd. Extending the Genève machine is effortless. It's easy to prove that if nu Wells dominates mu, the same is true for the Genève cone. It's the same proof. Products are trivial again, and the same proof lets you handle Gibbs measures. And if you have that mu dominates nu, then just by taking a single factor with a minus sign, you see that integrals of mu dominate integrals of nu. And this immediately implies that if you have measures on finite products, on individual spaces, which Wells dominate, and you take a Gibbs measure with a Hamiltonian whose negative is in the Genève cone of the unions, then the products measure it, and one has the corresponding inequality. In particular, if you take R nu, then what you discover is that for all, you get Ising domination of the corresponding measures. So Wells dominations implies Ising domination. It's a binary. I'm going to skip this slide too, I think, because of time. The slides, I was told, will be posted, so you can read the skip slides if you want. We say an even measure. So Wells proved one big theorem. We say a measure is non-trivial, an even measure if it's not a unit mass at 0. And what he proved is if you take any even probability measure that's not trivial, then there exists two strictly positive numbers, t minus and t plus. So whenever mu s is bigger, whenever s is bigger than t plus, the Bernoulli measure Bs dominates mu, Wells dominates mu, and whenever s is less than or equal to t minus, Bs is Wells dominated by mu, and t plus has a trivial formula. It's very easy to prove that. The essence of his proof is that t minus is essentially the largest number, so that you have the positivity of the following quantity. The proof is not hard, but I'll refer to either the preprint I discussed below or my book when it appears, or you can get a hold of Wells' thesis on ProQuest. One consequence of the theorem is that this t minus is always less than the second moment, and it's an interesting question about when one has equality. So one case to consider is the trivial case where so-called spin, well, not spin one, where I take a 3 points, 0 and plus or minus 1. This is a one parameter family. Since I want the measure to be even, you can compute what x squared minus t squared is. And by doing a little arithmetic, you discover that when lambda is less than a half, the t minus is the square root of lambda, which is indeed the second moment. But when lambda is bigger than a half, in fact, it's not the second moment. It's strictly smaller than the second moment. And in particular, the case where lambda is 2/3, which corresponds to equal weights at the 3 points, is not this case where you get the second moment. So I then started thinking about what happens for general spin S. So for general spin S, the most natural measure, if you rescale it, is you take 2s plus 1 equally spaced values between -1 and 1. You give them equal weights, and that's called the spin S Ising model. Often, in fact, you normalize it so that the maximum value is 2s. This is a scaled version of what is sometimes called spin S Ising. We've just seen that for spin 1, you don't have the second moment result. However, I quickly determined that one should expect equality in all the other cases. I didn't spin 3 halves by hand, and I used Mathematica to compute the corresponding objects for many values of m for various values of s, namely for 2, 5 halves, and 3, and I did 5 values for f. They were all positive. So Mathematica was telling me it's a good conjecture that for general spin S, this B minus of BT minus of Wells is the second moment, led to the natural conjecture, which one can write in the following form, where AS is the second moment. And I'll have more to say about this later, including that it's now a theorem. I'm going to skip this because of time. One of the things I want to note is I explained earlier that Wells domination gives you a lower bound on transition temperatures. It turns out Griffiths, in a famous paper that was mainly notable for extending correlation inequalities in Li-Yang to spin S Ising systems, but he also proved an inequality that is at the very bottom of that says that the spin S model is bounded by 1/4 the spin a half model. And I determined that one can improve this, one can improve the constant to this value if you could prove the conjecture. And you get this value for even in the case where S equals 1, where the conjecture, the analog of the conjecture is false. And this is an improvement by Griffiths of at least 4/3. The improved constant that's up there for S different from 1, we know is optimal because it's what you would get from mean field theory, and it's known in infinite dimension mean field theory is exact. Oh, the precise conjecture is a numeric conjecture of the following form, that if you take any S that's a half an integer and you form the sum that's sitting there, where when S is an integer, this is the usual sum, and where S is an odd integer, so that, for example, if S is 3/2, then I really want to take J equals minus 3/2, minus a half, and 3/2. So I take unit integral spacings from minus S to S. The conjecture says that these are all positive. I found this fascinating. I worked on it with no progress for about 7 months. I even had 3 of my co-authors on other papers think about it with no luck. They were very interested in it. Lieb has a celebrated paper on comparing Heisenberg models, admittedly classical versus quantum, not correlations, pressures, but given that this is a different kind of comparing correlations of different models, and I didn't want to bury this work, this result of Wells, in which had not been appeared for 45 years. It seemed natural for this to be in an article when I was asked to contribute to a Festschrift for Eliot's 90th birthday. Paper was due on January 31st last year, and on January 14th, I had a first draft. It seemed a shame not to make one more push to prove the conjecture. So I did the obvious thing. So I pause on the title here, because normally if you see something measures, singular measures, absolutely continuous measures, you think it means some class of measures. But of course, by desperate measures here, I mean something else. Desperate situations call for desperate measures. So at 11 a.m. on January 14th, I sent an email entitled The Challenge that stated the inequality with a draft to explain its significance to Terry Tao. When I logged on after Shabbos the next evening, I had an email dated 1:30. I didn't log on until 7:30 with a proof of the conjecture. But it wasn't quite as you imagine it. At 1:30 the day before, Terry had emailed me back. I have a postdoc who works on some inequalities vaguely of this type. I'll forward this problem to him and see if he's interested. And it was, in fact, the postdoc, Jose Madrid, who sent me the proof. His note had a wonderful idea, Karamata's inequality, that I'll describe, and 5 dense pages of calculation to implement it. We Zoomed several times, first for me to offer him a co-authorship. He had suggested an appendix. Terry had suggested an appendix, but it seemed co-author was appropriate. And to discuss simplifying the details, because if you know me, you know I wouldn't like 5 pages of dense calculations. We discovered a criteria for what's called majorization. I'll tell you what that is in a second. That led to a 3-line proof. Okay, 3 long lines, but basically 2 simple ideas and a very simple calculation. We then discovered that actually this simple proof only worked in the case that S was half an odd integer. The integral case is harder, that I may have time to explain. We found a proof in that case also that was only a little longer and less satisfactory for various reasons I'll get back to later. Jose suggested it would be a good idea to try locate wells again. I wasn't starting at ground zero. I'd gotten nothing from Indiana University, but I talked about this work in April of 2022 at a conference in honor of my 75th birthday. And Leonard Schulman, who's a computer scientist at Caltech and actually the son of a student of my advisor, Arthur Whiteman, heard my talk and did some Google searching and found a short story available via Kindle on Amazon, whose about the author read. Daniel R. Wells was born in Sterling, Illinois in March 15th, 1945. He attended local parochial schools and graduated from high school in 1963. In October of that year, he enlisted in the United States Navy, served for 4 years. After that, he started college in '68, studying mathematics, eventually earning a PhD from Indiana University in 1977. He taught mathematics for 2 years at Texas A&M and returned to school at the University of Illinois to study computer science. He achieved a PhD in '82 in computer science and worked for various companies as a software engineer until he retired in 2004. I wasn't clever enough to pull the right threads in this story. I had friends at Texas A&M, so I consulted them to see if they could find any record of him. No luck. I tried to leave a review of his book saying I wanted to contact the author about his thesis, but Amazon said it wasn't a review and they wouldn't post it. I bought his Kindle book, hoping it might provide more information, but it didn't. What I should have done is to contact the University of Illinois Computer Science, where he'd gotten his second PhD, and where it turns out he continued to do some teaching, but I didn't, and I would learn that later. But spurred by Jose, I posted a message on Facebook where I have a group of friends, mainly mathematicians and theoretical physicists. The message gave some background and asked if anyone had any idea how I could locate wells. A math grad student at Penn State told me he regarded himself as something of an internet sleuth. The next morning, I had a link in a private message from him to a find a person internet site with the right name, the right age, who lived in the town where the Amazon profile said Wells had born. And shortly after that, this student sent me what he thought might be Wells' email address. I contacted this email address asking if the recipient was the Daniel Wells who got a math PhD in Indiana, then sent him the current draft and asked him to be a co-author. After all, 2.5 sections of that were from his thesis that hadn't been published. He agreed. So in 1 week, the paper picked up 2 authors. In the next week, Jose and I Zoomed with Daniel, and I got some more background. Wells had gone to Texas A&M for a postdoc, written up his thesis with the addition of this Rotor-Ising comparison theorem that Eisenman and I had quoted, and he sent the preprint that Eisenman and I had referred to off to a journal that it definitely should have been accepted at, but it was ejected. At this point, his thesis advisor should have stepped in and explained the facts of life. Just as there are bad papers, there are sometimes bad referees, and one should send the paper off to another journal. In other words, he should have said, jerk, send it to another journal. But alas, Slim Sherman, his advisor, had passed away shortly after he'd finished his thesis, but before he took his oral exam even, and he wasn't there to advise him. And this was not in the nowadays postdocs have mentors. This was the bad old days. Postdocs didn't have mentors. He didn't have anyone at Texas A&M to sort of put an arm around his shoulder. And so he didn't know what to do. He was so discouraged, he totally left mathematics, even though the paper he'd written was really a very good thesis. Sometimes the system doesn't work. Lest you feel too bad, I noticed he retired in 2004. He told me that he actually spends most of his time now going on cruises. My impression is he got into some software business that meant he could retire quite comfortably. So leaving pure mathematics may not have been the worst thing in the world to happen to him. Okay, so in the 10 or 15 minutes that I have left, I'd like to explain the proof of this inequality, which I remind you says the following. I'm going to mainly talk about the proof when S is a half integer. Bigger than 3/2, because it's false when S is a half. And I'm going to prove for the half integral case, I'm going to prove this in fairly great generality. The 3j squared can be replaced by any even convex function. The constant SS plus 1 is exactly what you need for this to vanish when m equals 0. And the 2m plus 1 can be replaced by any odd function which is convex on the positive line. On the other hand, our proof when S is integral doesn't work if j squared is replaced by j to the p when p is between 1 and 3/2. So it's an interesting open question. Does the analog of this inequality hold for such p's if S is an integer? If S is a half integer, it does hold. And the key mathematical tool is the theory of majorization. The co-authors that I had worked on this with, I suspect, had never seen the theory of majorization, but I can't use that excuse because there's a whole chapter in my convexity book on majorization. So if you take majorization is defined as follows. You take 2 points in the positive authent of Rn. So we're going to take it this set where the x's are monotone decreasing and strictly positive. We say x majorizes y, written that way, if and only if the sum of all the coordinates are equal, and if I take the first n coordinates, the x's, remember they're ordered in monotone order, the partial sums are ordered in that way. And the key fact about majorization is y is majorized by x if and only if y is in the convex hull in Rn of the at most n factorial points obtained from x by permuting the coordinates. And this key fact is proven by slicing with specific hyperplanes and using the separating hyperplane theorem. So a very basic fact is Karapetyants inequality, which says the following: suppose x majorizes y and phi is an arbitrary continuous convex function on the positive reals, then in fact you get this inequality for the corresponding values of. It's widely referred to as Karapetyants inequality. It actually, or theorems like it appear in earlier papers of Schur and Hardy-Littlewood-Polya. It's simple. One proves the convex hull result I mentioned, and then notes that the function that takes W into this is convex and permutation symmetric. It's convex because phi is convex. And you therefore automatically get the result I quoted. The strategy of the proof when 2s is odd is straightforward. In that case, j equals 0 doesn't occur, right? For example, as I told you, you get minus 3/2, minus a half, 3/2. So every point that occurs, since you have an even function, since the j squared is there, you might as well just sum over j bigger than 0, because all that the negative j's do, you get the same value. They give you the same weight. So let x be the non-negative. You let x be the vector of non-negative numbers among the quantities. So the points where 3j squared minus the second moment is positive, you let x be the non-negative values written in decreasing order, and y the absolute values of the negative ones. And you prove there are more y's than x's. That's fairly easy. And you pair the x's with extra zeros if need be. That one has equality when m equals 0 implies part of what you need to prove majorization. So to prove that x is bigger than y, if you prove that, then because this function is convex at Karapetyants inequality, you immediately get the boxed equation. So you really just have to prove this majorization result. And the proof that x equals y relies on a new criteria for majorization that we found. It's the following lemma. Suppose you take 2 points where the sum of the coordinates are the same. And if you look at the difference, xj minus yj, it starts out positive and it changes sign only once. So suppose that's true, then x dominates y. Now I say this is a new criteria. It's new as far as I know, but there are books on majorization. There's a huge literature on majorization. I won't guarantee you this is new, although, as I said, I don't know, and I didn't find it when I skimmed some of the books on the subject. And the proof is really easy. When k is less than the point where the sign flips, because the x's are bigger than the y's, you get this. And if k is bigger than L, you've for the tails, you get this relation in the other direction because the inequality goes in the other direction. And if you take the tails and you subtract off from the fact that when the sums are equal for everything, you subtract, you get the inequality. And so majorization is immediate. So the key to proving the inequality in our case is proving this fact, that if you prove this difference is monotone decreasing, then obviously flip sign exactly once. That's the same as proving this inequality, which, given that this function is convex, is easy to prove. So it's really a very easy argument of the conjecture. When S is integral, it doesn't really work. You don't get one sign flip. For example, if you take S equals 7, you take S equals, 7, you get 2S, you get 15 values. So these are the values of the X's and Y's. And if you look carefully, it actually changes sign 3 times. But so the lemma doesn't work. But using the fact that the sum of the first 2 X's is bigger than the first 3 Y's allows one to prove the result. And there's a similar argument that works in general, but it's much uglier and requires really proving this extra fact. So that's my talk. But of course, I learned a long time ago that one should never avoid the opportunity to mock it. Many people, of course, know me because of the Reed-Simon books, but not everyone seems to have learned that now, 7 years ago, the AMS published a 5-volume set of books called A Comprehensive Course in Analysis that I highly recommend. There's real analysis, there's basic complex analysis, advanced complex analysis, harmonic analysis, and operator theory. You should think of it in the following way. It has twice as many pages as Reed-Simon, but because Reed-Simon is currently published by Elsevier, it's half the price. So for half the price of you get twice as many pages, but of course not the same material quite. And finally, I have one more recent book. So thank you for your attention. And I'll be glad to take questions.
Thank you, Professor Simon, for very exciting and very interesting talk. And we have time for questions. So please, if anyone has a question, you can raise your hand. Maybe I'll have small question. You see, in the inequality for the measures, when you use a measure for mu and nu, can this measure be discrete? So can you just go to the discrete case?
Well, I consider the discrete case. I was talking about the case where the were ordered at 2s plus 1 point. So I've been the case is that one, in fact, in the early days, one only considered this discrete spin S case. But the work that Griffiths and I did, and that Guerra, Rosen, and I did, that approximated quantum field theories by continuous spins, increased the interest in continuous spins. So, but the discrete case, special case, yes, you can certainly. It doesn't simplify particularly in the discrete case.
So, but it's inside of this calculus, right?
Yes.
Okay. And also you start with general measurable functions, but then you go to convex Hill of.
So you need something, and in general, one can consider families of measurable functions, but in all practical applications, in fact, you're only considering polynomials. You're considering.
Yeah, that's what I'm asking. Would it be easier to start with polynomials and to prove something for the?
You might think that, but I don't. The answer is the machine works just as well for arbitrary functions. When you actually want to compute, you specialize to polynomials. So in some sense, the paper of Van Byron and Sylvester that I talked about, instead of considering polynomials, considers arbitrary convex functions that are complex and monotone that are odd and convex. And if you do that, the condition you get turns out to be so strong that minus, that's the weakness of what they do. So but the abstract machine works for general function. I don't know of anything better you learn by restricting to polynomials. But if you actually want to prove, so the conjecture that I talked about is specifically where you specialize to polynomials.
Okay, maybe just one more question about the complex structure. Can this be generalized for complex analysis somehow?
So complex analytic techniques can be useful, but again, positivity and complexity. The answer is I don't know any reasonable way.
Okay. So we have question by Ike Urdaglan. I don't know. Can you hear us, Ike?
Yes.
Please go ahead.
Thank you. I have some question about the sum in the final of your presentation.
The sum in what?
In the end of your presentation.
The sum that's in the box?
Yeah. Yes.
Okay.
I don't understand why. What is the problem with this sum? And is that we can replace it by the sum with m in its limits instead of s?
The conjecture. So, for example, when s is a half, so there are really just two terms in the sum. In fact, the sum is not positive for any m other than m equals 0. It has the wrong sign in that case. But by this seemed to be right. It means that you don't have the second moment property. But by doing some experiments with Mathematica, I discovered it seemed to always be positive when s wasn't half. It was a larger sum. So there's obviously something non-trivial to prove. Some of these terms up, right? Because the sum of all these terms is 0. If I take m equals 0, the sum is 0. So there are some positive terms and some negative terms.
Yes, but I'm sorry. This is the sum of polynomial, yeah?
It's a sum of
even polynomial.
No, well, of even polynomials. Yes, it's in fact It's a polynomial, correct?
Polynomial regarding to G.
But you're taking the sum of the polynomial at a certain set of points. And we know that at some of the points in the sum, the terms are negative and some of them are positive. The conjecture is that the overall sum is for, at least when S is bigger than a half, it's the sum is positive, but you're taking a polynomial that's in some places positive, some places negative, and you want to know these sums. It's a relation about finite sums that turns out to have interesting consequences because it tells you something about relations between critical temperatures in these models.
Thank you. And one more question, please.
Yes.
Okay. Why we need the symmetric limits of the sum? Because the sequence on the sum is even, they say.
I don't understand.
Why we consider the sum from minus S to S instead of the sum from 0 to S, double sum?
Well, if S is a half integer, then in fact the terms are symmetric. So whether you sum from minus S to S or from 0 to S is the same. And we actually use that in the proof. The thing that's different when S is an integer. So if you say take S equals 1, so there are now 3 values, -1, 0, and +1. The -1 +1 combination occurs twice. The S equals 0 occurs only once. So when S is an integer, you can start the sum as 0, but then you only are allowed to take half of the lowest term. You don't get to.
Okay. Okay, thank you.
Okay. Thank you. So we have one more question by Dmitry Karp. Dmitry, can you hear us?
Can you hear me now?
Yes, please go ahead.
Yep. Barry, hi, Dmitry Karp. I have a kind of general question about this last part as well. Does your proof for the case when you cannot apply one change of sign lemma, can this proof be translated into some general statement about majorization?
Yes.
So can you make it another lemma which is not one change of sign?
There is a result, a general result you can state, but it requires an extra inequality on the. So if you think of the J as being, there are 2 functions underlying. The J squared, which you might call psi, and the x to the 2m plus 1, which I might call phi. So in the spin a half case, there is the result holds for an arbitrary convex function, even convex function psi, which replaces the J squared, and an arbitrary convex on the positives odd function that replaces the 2m plus 1.
Mm-hmm.
If S is an integer, there's again a majorization result. But you need an extra inequality on psi. It isn't enough that psi just be convex. It's some, I don't remember what it is, but if you look in our published paper, we actually stated in this general.
Okay.
But
yep.
For our argument to work, you need an extra condition on psi. That condition does not hold for this x to the p when p is between 1 and 3/2. It could be the inequality still holds. We just have the wrong proof.
But you haven't shown the reference to the published work, but probably it's easy to find, right?
I'm sorry, the published paper, yeah, I didn't, yes. So it's in fact, if I'm sharing.
Yeah, but it's probably easy to Google.
If you go to my webpage,
yeah, thanks. No problem. Yeah, for sure.
It's the lead festschrift. So if you go to Google Scholar and you just look up Madrid and Simon, you'll find the paper. But it's in the festschrift, which was published by the European Math Society about a year ago. It's in volume 2 of the festschrift.
Okay, whatever. Yeah, thank you. I got it. Thank you very much.
But there's the preprint is also available. In fact, it's a secret. All my papers are pirated and posted on my website if anyone wants to download it. I asked my librarian if I could do it. She said, if anyone complains, Caltech will force you to take it down. But no one will complain because they'd be too embarrassed to complain that the author is posting his paper. Although technically I turned over copyright to
for sure. Yeah, for sure.
But
okay, thank you very much. Got it.
If you go to my webpage, you can get any of my papers there.
Okay. So we have one more question by Hera, if I pronounce correctly.
Yeah. So yeah, thanks for a nice talk. So I think my internet was not the best, so I might have missed this. But quick question was if the lemma you stated on majorization, right? If you can go to that.
Yes.
The new.
This one.
Yeah. So sorry, is the converse true?
No, certainly not. There are many cases where it majorizes where this is not true. No.
Sort of varies.
Trivial to write down examples where, in fact, in our case for the integral case. So if I go back to this case that's written explicitly, and I move the 0 to the to sit. Well, in fact, this X majorizes Y, even though the lemma doesn't apply here. But it is true that X majorizes Y in this case.
Okay.
This has 3 sign flips, not 1 sign flip.
That has 3 sign flips. Okay, sorry, I missed it.
Flips, right? The difference flips from it's negative here, but then it's positive again till it turns.
Okay, I see. There's a sign flip. Okay, yeah, sure. Thank you.
Okay, thank you. More questions, please. So meanwhile, may I have one more question? I was wondering about the person, it names Wales, I guess. The person who was from IT business, you have been searching for this person, then you found him and wrote a paper with him. But he was out of mathematics, out of business for many years, maybe.
Correct.
So do you consider he practiced mathematics, so he was interested in continue in mathematics?
Well, he did computer science, which of course is a close area, but my impression is he actually did coding and software development.
Yeah.
I don't know any, and he actually taught a course in the computer science department on the side because he wanted to somehow, he liked the academic world a little bit. So
yeah, because it was very surprising. You see, when you told us this story, like you found a person who didn't do mathematics for many years, but then you had some conversation with him and he continues to do some research.
Not really. Not really. So he didn't do mathematical research. He has one published paper now. He used to have zero, but the paper with Madrid and me is his one published paper in his life is in mathematics. He may have a computer science paper. I actually suspect he does have some computer science papers.
But I still consider that this is a really wonderful story, for someone who did his PhD, and then after years, someone contacts him and says that your results.
I like the story but it's a sad story, and I even have a conjecture who I've been meaning to. I know the editor of the journal in question, and I won't tell you who it is. And I even have a conjecture of who the referee is, and I think I know why it got rejected, but it shouldn't have been rejected.
Yeah, but I'm saying that it's an amazing story. The guy should be honored very happy of having this notice.
He was clearly very pleased that he was reluctant to become a co-author because he didn't feel and I said, look, the basic formalism of the paper is yours. How would you not be a co-author?
So maybe it's a good scenario for a movie or short movie, maybe.
So that's a little bit too dramatic, but yeah, it's why I like to talk, because it's such a nice story.
But you did a great talk with this mentioning this history. It's a really good talk. Really good to know this.
And it's remarkable that Terry, not surprisingly, Terry was the right person to contact, although. And, it's fortunate Terry knows me. I'm sure Terry gets a huge amount of email that he ignores.
Yeah.
But at least he paid enough attention to forward it to his postdoc, who's a very sweet guy. Is just starting an assistant professorship this year in, he was a postdoc in UCLA, and then he spent a year in Geneva, and he just moved to Virginia Tech, where I think he's really quite talented.
Where is he from?
He also is an interesting story. He started out as essentially a peasant in Honduras. So he started out in some little village in Honduras, went to university, went to college in Honduras, did well enough in mathematics that he could go to IMPA in Brazil for a PhD, and got noticed by Terry and became Terry's postdoc. So that's also a great story. It's somebody who grew up in essentially a poor village in Honduras, and they're two co-authors, but I'm sort of there are nice stories on both of them.
Yeah, you see, your story can motivate young people who did receive rejection for a journal and think, okay, I'm not so good at mathematics, but then if they listen to your story, they think maybe it's not the time not good, maybe it's a kind of
well, I have another way of helping convince them. I remember once, probably 8 or 9 years into my career, when I was already famous, he said modestly, and Rene Carmona was visiting me, and he heard me complain that I just had a paper rejected. And I looked at him, I said, Rene, I've had more papers rejected than you've had accepted. There are many bad referees out there. It's hard. Being a journal editor is hard, and you send it to the wrong referee who instead of writing and says, I don't really understand this well enough, rejects the paper, or has. So my favorite rejection story, I have 2 rejection stories to tell you. So Elliot Lieb and I wrote a famous paper on Thomas Fermi that was famous enough that there was a conference on its 45th anniversary that the chemists had. It was on the large Z limit of atoms. We sent it off to physical review letters, and it got rejected. And the rejection letter said, "This is one of the worst papers I've ever read. It's a sequence of unproven assertions," which is true. It was an announcement, many of which are obviously false. For example, the authors say the Thomas Fermi density rho is C super infinity. That would make rho identically 0, 1, or infinity, depending on the value of C. So this was refereed by some theoretical physicist who didn't even know what the symbol C infinity meant. He thought it meant take C to the power of infinity instead of it being C infinitely smooth. In that case, we didn't send it to another journal. We actually complained to the journal in question, and I believe Freeman Dyson was the second referee and recommended acceptance. My other favorite story is much more recent, where with two co-authors we settled a 40-year-old conjecture of Whittam and sent it off to Journal X because one of my co-authors was interested in publishing Journal X. It's a fairly prestigious journal. And we got it back and said, it's very nice to have a paper that proves a 40-year-old conjecture, but the proof is too simple, so it doesn't belong in this outstanding journal. And so we sent it off to a more prestigious journal, to Invenciones, and it got accepted. So, anyone who gets papers rejected should know everyone gets papers rejected. And
thank you for so many encouraging stories.
Yes,
Anyhow,
thank you very much.
And
Thank you very much.
But,
Thank you very much.
Still, I have one more inquiry. You told us about your recent book, 5-volume book, right? But you also said that there is a new book on Go that will appear soon, right?
No. There's one that has appeared since. That's the last one, the last slide. This book is out.
Yes, I understood. But
there's a book I'm in the middle of writing, and I can't tell you. I can't tell you. So
okay.
Many of my books have been written in 2 to 3 years. I've already been working on this book for 3 years. If I had to guess, it'll go to the publisher in about a year. It's a hard book to write in many ways. And it's a little too long. I told the publisher it would be 350 pages. It looks like it'll be 700. But it's a very nice book. I always think the book I'm writing is the best book, but this one really is the best book. The one on it's called Phase Transitions and the Theory of Lattice Gas is going to be published by Cambridge Press. And my guess is it'll be out, if we're lucky, 18 months from now. Maybe if the publisher really tries in 2024, but I can't be sure. I haven't finished writing it, and there's some. The problem is I'm writing about stuff that people didn't write up very well, so I'm having trouble. You can't write about proofs of theorems if you can't understand what the proof is. Well, you sometimes figure out your own proof,
okay. We will be looking forward for your new book. Thank you. So Vladislav Kravchenko is here, my co-organizer of the seminar, and really happy that you agreed to deliver such a nice talk. And I believe that all participants of the seminar are very happy to hear this nice story. So thank you very much. Let all of applause.
Thank you very much.
Thank you very much.
Thank you very much for a very exciting talk. And we, of course, will post your video on our site and also a presentation. Thank you.